So we're going to examine now another change of coordinates, or rather integration in change of coordinates that has to do with triple integrals. And without any further delay, let us introduce cylindrical coordinates. So think about it this way. Cartesian coordinates, in the case of R3, is a set of three numbers that describe the position of a point. And cylindrical coordinates are going to also be three numbers that describe the position of a point, and they can be described, they can be given as follows. So imagine that you have a point. There are a few ways of introducing cylindrical coordinates, but here's the simplest one. So take the point that you have, so let's say this is your point, and project it onto the XY plane. What that means is take the line that goes through that point and is perpendicular to the XY plane and take its intersection with the XY plane. So once you do that, remember that this is the x-axis, this is the y-axis, and this is the z-axis. Find the polar coordinates of that point. So you will have the polar coordinate, the length r of the radial segment that connects your point, or rather the projection of your point, with the origin, and the angle theta, which is the angle of the radial segment with a positive x-axis. These are the first two cylindrical coordinates. And the last cylindrical coordinate is z. So the usual z that you have in Cartesian coordinates. So the cylindrical coordinates are r, theta, and z. And we can write down the formulas that give us the way to go back and forth between cylindrical and Cartesian coordinates. So x is r cosine theta, y is r sine theta, and z. Okay, this is not much of a formula. And of course, we shouldn't forget here that we also have the very interesting connection that x squared plus y squared is equal to r squared. So now, what else do we need? So we described the cylindrical coordinates. That should allow us to describe our sets. Remember, that's the first step of changing an integral into a different set of coordinates. Then we have the second step, where we need to change the integrand to express it in terms of the new coordinates. And of course, that is done by using the formulas that we just gave. And last but not least, the last step is the Jacobian, the distortion factor, that tells us how the volumes of small boxes with dimensions delta r, delta theta, and delta z can be expressed. And here, let's think about it. I mean, if you think about it, in the x and y direction, what you really do is you're taking polar coordinates, and you know that the distortion there is r, right? In the z direction, you just use the common coordinate z. So there is no distortion in the z direction. So guess what? If you guessed it, then that's great. The Jacobian is none other than r. Okay, so now we have all the ingredients that we need. And let's begin with an example. Okay, so compute the integral. So triple integral over u of zd v, where u is the part of the cylinder x squared plus y squared less than or equal to 1, that lies between the planes z equals 1 and z equals 2. Okay, let's try to sketch this. Let's see what it looks like. So what I'm saying is that you have this cylinder that has radius 1 and it's centered around, and you're taking the portion of it that goes from height 1 to height 2. So this is, if you like, your region right here. This is the part that we're interested in, and we could write it as u to be all the r thetas and z's, such that, let's think about it. So r, if you project this onto the xy plane, you get a disk. So the unit disk actually. So r is between 0 and 1, and theta is between 0 and 2 pi, and z is going to be between 1 and 2. So we get a very nice domain, and the computation now can proceed as follows. So we will take our triple integral, and we first take care of the domain, so that's step 1. So we will go 0 to 1 dr, 0 to 2 pi d theta, and 0 and 1 to 2, sorry, 1 to 2 dz. So we get a box, right? I mean, from such a domain that is certainly far from being a box in Cartesian coordinates, we get a box in cylindrical coordinates, which means that this becomes quite convenient for us. So that's step 1. Step 2 is the integrand. The integrand is the easiest thing in the world, because z is a valid cylindrical coordinate. There's nothing to change. The only thing we shouldn't forget is r, which is the Jacobian. That's step 3. And of course, now it splits. It splits. Why? Because all of your endpoints are constant, and the integrand is a product of quantities in the respective variables. So how does it split? It's 0 to 1 r dr, right? And then it's 0 to 2 pi d theta. I'm writing d theta because there's no explicit use of the variable theta in here. And finally, it's 1 to 2 z dz. All of these are quite simple integrals to compute. So for r, the antiderivative is r squared over 2. You want to go from 0 to 1, and that gives you 1/2. For the middle integral, it's just the length of the interval, so it's 2 pi. And for the last one is again z squared over 2, but this time you want to go from 1 to 2, so it's 4 minus 1 is 3/2, 3 over 2. Okay, multiply them all together and find the final answer, which is, what is it? I don't know. It's 3 pi over 2. That's the final answer. Okay, if you multiply the numbers 1/2 times 2 pi, that gives you pi, and pi times 3/2 is 3 pi over 2. And that's it, right? Very, very pleasant. Okay, let's do another. Let's do another one, see if we can get the hang of this. And our next example, let's see if we can find a better, a more exotic domain. So compute the triple integral over u of, let's make it a little more interesting now. Let's take x squared dv, where U is the part of the cylinder x squared plus y squared is less than or equal to 9 between z equals 0 and z equals 2, that lies in the first octant. So we have 8 octants, and to be honest with you, I'm not sure I know the enumeration of the 8 octants, but the first one is the one where all coordinates are greater than 0. So there can be no doubt about that, and that's the only thing that we need here. So I could have specified this obviously differently by just saying that it's the octant defined by, or it's the region for which x is greater than 0, y is greater than 0, and z is greater than 0. But let's try to sketch this. Let's see what we have here. So it's not even necessary to sketch it, but you know, it's good practice to do so. So I want to go from z equals, so let's say let me draw these two vertical lines. So this way I draw just the part which is in the first octant, and I set this to be 2 and this to be 0 right here. So that's the region that we're looking at. And if we want to describe it in terms of cylindrical coordinates, it's again very, very straightforward. It's all the r thetas and z's. And here, you know, before I complete this description, it's a good idea to understand that how cylindrical coordinates work. It's as if you split the whole three-dimensional space into horizontal planes that are referenced by the z coordinate, meaning the height at which they lie. And on each of these planes, you take polar coordinates, r and theta. That's one way to visualize and embrace cylindrical coordinates. So r here is between 0 and 3. Why is that? Because we see that the boundary of the cylinder is given by x squared plus y squared is equal to 9. And here, I should say that when I say cylinder here, I mean a solid cylinder, meaning including the interior. I don't think that there is a terminology. There could be. I mean, I'm thinking of the word tube now, but I'm not sure there is a terminology that distinguishes between a solid cylinder and just the surface. But here, obviously, when I take the inequality, I mean the interior of it. And theta is not going all around this time, right? So theta is simply going from 0 to pi over 2 because we're in the first octant, and the first octant projects onto the first quadrant. And finally, z is between 0 and 2. And I think we have everything that we need. So let's see how this integral is going to be computed, and let's hope that we're going to have a much more interesting computation here. So we have the triple integral of x squared dv over u. So this is going to give us, so first take care of the domain, right? So dr, where r goes from 0 to 3, and d theta, where theta goes from 0 to pi over 2, and dz, where z goes from 0 to 2. And then we will have x squared, which is r squared cosine square of theta. And finally, so that's our integrants. That's step 2. And let's not forget step 3, that is the Jacobian, which is r. Okay, this integral, guess what? I mean, it becomes almost boring, right? It splits again. And we're going to get the integral from 0 to 3 of r cubed dr times the integral from 0 to pi over 2 of cosine square of theta d theta. And finally, we will have the integral from 0 to 2 dz. So, okay, let's integrate those things. So the first integral is very simple. It's r to the 4th over 4. You want to go from 0 to 3. That will give you 81 over 4. Okay. The last integral is 2. You're integrating the function 1. You're just getting the length of the interval. The middle one is the interesting one, right? To integrate the middle one, let's use the double angle formula that tells us that cosine of 2 theta is cosine square of theta minus sine square of theta, which is the same thing as by using the Pythagorean theorem as 2 cosine square of theta minus 1. And if you solve for cosine square of theta, then you get cosine of 2 theta plus 1 over 2. I mean, you may want to just remember this formula. I usually want to just remember the double angle formula and deduce everything I know, because now I need to just integrate this. And what is the antiderivative of this? So the other antiderivative of this will be sine of 2 theta over 4 plus theta over 2. And you want to go 0 to pi over 2. And here's the interesting thing that happens. If you plug in 0 into sine of 2 theta, you get sine of 0, which is 0, right? So nothing much here. If you plug in pi over 2, then you get sine of pi, which is again 0. So the sine of 2 theta over 4 doesn't contribute anything. And the only thing that you need is to compute theta over 2 from 0 to pi over 2. And that, of course, gives you pi over 4. And when we put together all of this, we get something like 81 pi over 8, I guess, because on the denominator we get a 16. There's these 2 right here, so that should be it. Okay. Okay. Let's do another one. So this time, let's try to get something which is not a cylinder, which will have a little more something a little more interesting to work with. So let's do the following. Example. So compute. Let's do a volume. Okay, let's do a volume. So compute the volume of the solid that is inside the cylinder x squared plus y squared is, you can't say is equal to 1. I mean, I keep saying less than or equal to 1. I could say is equal to 1. And is bounded below by the xy plane and above, it's bounded above by the plane. Let's take a more interesting plane now. So x plus y plus z is equal to 3. Let's take 3. Okay, so let's try to understand what is going on here. So what do we have? So you have your, let's call it unit cylinder. I'm not sure this is a very common way of calling this cylinder that projects onto the unit disk. But what is happening now is that you're coming down with a plane this plane here that is cutting the cylinder in an oblique way, and pretty much what you get is, I mean, the top side is really an ellipse. That's what you're getting, and this is u. And this is where things become a little more interesting. This is not a box anymore. I'm sorry. This will not be a box in cylindrical coordinates. So let's try to write down what this is. So the simplest way to do this is to try to proceed first in the vertical direction. So z will be between 0 and what else? If you solve for z here, you will get that it's 3 minus x minus y, but you shouldn't be using x and y, right? You should be using their expressions in terms of r and theta. So 3 minus r cosine theta minus r sine theta. And of course, r is between 0 and 1, and theta is between 0 and 2 pi. These are domains. So it's certainly not a box with respect to cylindrical coordinates. And you want to find the volume of u, which means that you want to take the triple integral of the function 1, right? So the integrand is the function 1, and when you say you have the function 1, it's the function 1 regardless of what coordinates you're working with. So this will be what? Let's start with the domain. So the domain will be from 0 to 3 minus r cosine theta minus r sine theta dz. And then r is going to run from 0 to 1, and theta is going to run from 0 to 2 pi. Your integrand is the function 1. That's step 2, and your Jacobian is r. And now we know what we have to do here. So let's carry out the first integration. The first integration is with respect to z, and r is constant. So what you're going to get is the integral from 0 to 2 pi times the integral from 0 to 1, or no, I'm sorry, not times, I mean, in an iterated way. And then you have rz that goes from 0 to 3 minus r cosine theta minus r sine theta. And this is d r d theta. And this is going to be the integral from 0 to 2 pi, integral from 0 to 1, 3r minus r squared cosine theta minus r squared sine theta dr d theta. Okay, well, this integral still doesn't split, but if you decompose it into a sum of 3 integrals, each of those 3 integrals will split. So I can write this as the integral from 0 to 2 pi of and from 0 to 1 of 3r dr d theta minus the integral from 0 to 2 pi integral from 0 to 1 r squared cosine theta dr d theta minus the integral from 0 to 2 pi integral from 0 to 1 r squared sine theta dr d theta. And now each of these 3 integrals actually split. So the first one will be the integral from 0 to 1. I can take the 3 out, right? 3 is a constant r dr times the integral from 0 to 2 pi d theta minus the integral from 0 to 1 r squared dr times, you see how interesting this principle, how useful it is even in cases where you wouldn't expect a splitting, at least right away, you do get a splitting. And you will see how else this is going to be useful. So 0 to 1 r squared dr times 0 to 2 pi sine theta d theta. So here's the really interesting stuff. With the integral of cosine of theta, I mean, you can think of it any way you like, but from 0 to 2 pi, it has an equal amount of positive areas as it has negative areas, or rather you can also take a look at the antiderivative, which is sine theta. From 0 to 2 pi, you get 0. So this whole thing is 0, which means I don't care what anything else is here, even though it's easy to find each 1/3, and that part is 0. So this is 0, this is 0. I don't care about these things anymore. And this is r squared over 2 from 0 to 1, which is 1/2. This obviously 2 pi, and I have also the 3. So the final answer is 2 pi times 1/2 is pi, so it's 3 pi. Okay, and 3 pi is actually quite interesting. If you think for a second, you will realize that we would have found the same answer if we took the cylinder that went from z equals 0 to z equals 3. It doesn't really matter that we took that plane, which went in an oblique way, because if you look carefully, you will realize that because of symmetry, it would have been the same as if you cut by a horizontal plane, even though you don't need to realize that. This problem is already interesting enough as it is. Okay, and we would like to finish with one last example, and let's do something really cool now. Again, it's not going to be a box once you transform it in polar, in cylindrical coordinates, but it's going to be a very, very interesting example. It's going to give us the volume of the sphere. So use integration in cylindrical coordinates in order to find the volume. I said sphere, I want to say ball. Remember, it's the usual distinction when we talk about sphere, it's just the boundary. When we talk about the ball, it includes the interior. The volume of the ball of radius r. And of course, we can take the ball that is centered at the origin, even though it's not being given explicitly that we should do that. So the question is, how do you express the ball of radius r in terms of cylindrical coordinates? And again, it's not going to be a box in cylindrical coordinates. You're not going to get a constant endpoint. So what do you get? So first of all, so r, theta, and z, where z is going from the lower hemisphere to the upper hemisphere. Now, what's the lower hemisphere? Let's think about it. Or what's the whole sphere, actually? It's x squared plus y squared plus z squared is equal to r squared, right? But now you have the nice thing that x squared plus y squared, as we said, is r squared. So this gives you z squared is equal to capital R squared minus little r squared, where you have to realize that r is a constant, uppercase r is a constant. Little r is just our parameter. Okay, so the status of these two letters is completely different here. And we're going to get that z is, of course, plus or minus square root of r squared minus little r squared. And that are going to be the lower and the upper. So it's going to be minus square root of upper r squared minus lower r squared, and positive r squared minus little r squared. The rest is easy because you're in the disk, inside the disk of radius r. So little r is going to be from 0 to r, and theta is going all around, and that's your domain. So the volume of u is going to be the triple integral of the function 1, right? So let's put the correct endpoint. So we're going to have negative square root of r squared minus little r squared to square root of r squared minus r squared. That is going to be dz, right? And then from 0 to r dr and from 0 to 2 pi d theta. So the integrand is 1, and that doesn't change. And step 3, don't forget your Jacobian, which is r. And that gives us what we want. And the first integration will be z because zr, because r is constant with respect to z, and we will go from negative square root of r squared minus little r squared, square root of uppercase r squared minus lowercase r squared, and we want to go from 0 to r dr, and then from 0 to 2 pi d theta. And this, of course, is going to give us zr. The z is going to actually be replaced. So it's going to be r times square root of r squared minus minus itself. So it will be 2r square root of r squared minus little r squared. This goes from 0 to r dr. This goes from 0 to 2 pi d theta. This integral obviously at this point splits, but no need to do anything here. Let's just do a substitution, which is rather instructive. So we're going to take u to be r squared, r uppercase squared minus r lowercase squared, and du is going to be minus 2r dr, and r dr, or 2r dr, which is what we have, is going to be minus du, right? So what are we going to have? Let's take that minus sign outside, 0 to 2 pi, and we're going to have square root of u du. And now the interesting part is, what are the endpoints? To find the endpoints, we're supposed to take the old endpoints and plug them into the substitution, right? So when we plug in uppercase r, we get uppercase r squared minus uppercase r squared, which gives us 0 on the top. And when we plug in 0, we get uppercase r squared. Okay, and this is now d theta. Okay, and the nice thing is that the minus sign that we have in front can bring our endpoints, our limits in the inner integral back to their natural order. And the antiderivative of u, which is u to the 1/2, is 2/3 u to the 3/2, and we will go from 0 to r squared. And this whole thing has to be integrated once we find this number from 0 to 2 pi d theta. I could have split this integral, I didn't do it. Now, when you plug in r squared in u to the 3/2, what do you get? You get r squared to the 3/2, which is r cubed, right? Let's see this, r squared to the 3/2, which is like multiplying with 3/2 on the exponent, that gives you r cubed. So what you get is 2/3 r cubed, right? Minus the other part, which is 0. And then you're going to integrate this function, which is constant with respect to theta, from 0 to 2 pi. So you're going to get 2/3 r cubed times the length of the interval, which is 2 pi, which gives you 4/3 pi r cubed. I think that many of you might already know this formula that gives us the formula of the volume of the ball of radius r. Okay, and that's all there is to it. Cylindrical coordinates are a lot of fun. I hope you had some fun, and thanks for watching.